Good evening, everyone. So, today is the fourth week of the NPTEL class of microwave remote sensing in hydrology. I'll be covering few topics today. The first one will be the Doppler shift that happens in radar. So, we know the Doppler effect that happens, it is mostly related to the sound wave, as we know that if the sound source is moving, we get the sound effect increasing or decreasing. Like from us, if the sound source is moving away, the increasing the sound gets, the frequency gets increased, and moving away it gets decreased, and when it's moving towards us, comes closer to the source, then it gets increased. That is called this change in Doppler effect due to the target, due to the motion of the target or the observer, anyone or the both. That is called the Doppler effect. So the Doppler effect, how that is related in the radar, what it does. So as we know the radar, how the aircraft and the target, there is some motion. So for radar, sometimes the observer is standing, the target in motion. Sometimes the observer or the antenna is in motion, the target is in stand. So it depends on different cases. For us, what we consider for remote sensing perspective and to detect ground target and objectives, remote sensing perspective, we are mostly focused with the when the antenna or observer is in motion, our target, that is the earth surface, is stable. But also another aspect is also there, that is the MTI radar, that is the moving target, to detect target, or suppose in security surveillance purpose to detect the one vehicle or any intruder that is that has some movement. That time also radar, the surveillance radar, these things come useful. So that has some another, but for both of the cases, the Doppler effect that comes in the case. So the as per theory, the Doppler shift occurs due to the relative motion between the source sensor and the target. So source sensor or the antenna can be in motion, the target can be fixed, or the target can be in motion, the sensor can be fixed, or both can be in motion, the sensor and the target. So as the satellite moves, the frequency of the transmitted signal appears to change when reflected from targets. The shift is positive when the satellite approaches the target, that is the frequency gets increased, and negative when moving away, so frequency gets decreased. What are the causes? That is the platform motion, the primary cause. Platform in the sense the sensor that resides on the platform, that is called antenna. It can be antenna also one part. So platform is suppose the flight or the satellite. So the platform it moves. For us, suppose the flight, it moves. So it gets the Doppler effect of the satellite, many satellites. Satellite's orbital velocity. The satellite, it has its own velocity also. So it has that velocity because of that also. And Earth's rotation effect. There are many rotation or many velocities. The Earth velocity and the satellite velocity, all other are working together. So it all are not at same velocity. It has different velocity. So Earth is rotating at some velocity, and satellite is rotating or orbiting in some different velocity. So due to that also, difference in velocity also, the Doppler effect, it happens. And another is target motion, moving objects on ground. So depends on the, suppose moving vehicle, any moving you want to detect using SAR signal. Ocean currents or wind driven features. Ocean currents also, SAR is useful for different domain, surveillance and atmospheric use, and our earth surface. So all have whatever is in motion or the antenna is in motion. So due to the motion velocity for the both, it can happen. There are some atmospheric effects, so obviously because of the different atmospheric layers, troposphere delay, all those things. So those cause the different errors. If we can see the diagram, how and why Doppler effect actually for our case, when the target is stable and our antenna or platform is moving, that is our satellite or flight. So if we see, this is the ground and this is the ground track, you can see you can say this as azimuthal direction, and the flight is moving from this way, so satellite flight path, and it is moving, suppose, from here to this side. This is the nadir direction, the perpendicular direction. So from this point, it sends signal and transmits the signal to ground and receives the signal, and doing that thing, it moves along the path, along the azimuthal direction. So what there will be the frequency change because of this movement. It is staying stable and it is moving, so it will change because this angular distance is getting changed. This is the least distance when it is nadir, and when there is some angle, obviously it increase. So when moving this point towards this point, the angle or the distance gets decrease, then again when moving away, so the frequency is supposed to also will increase when coming to nadir point, then again it will decrease. This is how satellite works. So that is how the Doppler effect. So when we plot this frequency plot, Doppler frequency, the frequency will come like this, because as I said that here it is zero Doppler, because there it is in nadir direction and same point. It has zero, it is it zero, the difference in velocity just on this point. And as we come to this point, the frequency gets increase, then again decrease. So this is how the plots. And phase history. So if you notice the terms, the equation to the this Doppler frequency, it is called that frequency, it is called the Doppler frequency because the frequency gets increase and decrease. And how we modulate that frequency, we can't work with that increasing and decreasing frequency, so we modulate that. There is one called modulator, so we modulate that frequency. And other parameters are these beam width, squint angle, PRF, pulse repetition frequency, bandwidth, that are important to understand this diagram. Phase history also. So phase history, how this is the phase is like how it is changing its path, the signal or the wave, how it is changing. So it comes like in this form. What are the impacts? Okay, when we are into, we are learning SAR in remote sensing perspective, we are we should understand the basics, the numericals and the equations, but we should understand the numericals and equation in terms of physical terms, so that we can apply that. So physically, what are the effects, and what happens, and how we, overcome those issues like that. So what are the impacts due to the Doppler shift? It affects the azimuth resolution. Obviously, when we are dealing with frequency, that is called, that relates to the wavelength. Okay, and that is, directly related to our resolution, or that size, pixel size. And along the azimuth, it the Doppler, this along this it happens. So frequency also along the azimuth direction, frequency change happens. So there the azimuth resolution also gets affected. It creates phase shifts in the signal. It creates phase shifts because of the different position it is taking. The platform is moving, and it is taking different position, and the first position where it is receiving, it is, it is transmitting one signal and receiving that signal from second position. That is the principle of SAR. And from second position, whatever signal it is transmitting, it receives that signal from third position. So you are getting a phase shift. Suppose the first position, when you are first position, but you are getting or receiving the transmitted signal in your second position. So there is some phase shift. Phase you can say physically, just you can understand like the distance it is traveling. So suppose it is the first position, this point, and this is the second position. The distance it is traveling, suppose from here, and from here it is the different, okay, the objects. And so the phase also, the signal transmitting and when receiving, the signal has some extra part it will have. So that calls that results into the phase shifting. And if you remember, I told you that the matched filter has purpose. It has that thing to match the phase. So, and due to the Doppler, it can cause image blurring or ghosting. There is the term blurring, okay, but ghosting also is a technical term in terms of SAR. When you study about the radar image and radar signal, its impact, there is called one ghost image and ghosting. So this one is technical term. And radar images, it gets several, gets affected by several reasons. We will study all those speckle, clutter, noise, and also due to the Doppler shift, it gets some kind of image, blurred image, and some portion, different portions, that is called ghosting or blurring. It influences precise positioning of targets. Obviously, it will be difficult to to locate the exact position of the targets. There are few methods to handle this. These methods are like Doppler centroid method, motion compensation, all those. The processing technique is range Doppler algorithm that we work, and calibration approaches using corner reflectors that we use that, apply radiometric calibration that we use, implement phase calibration that also we do. And advanced solution are multi-looking processing. We do multi-looking. The multi-looking has purpose not only this, it caters into different, it caters into, it is useful for some sort of that noise filtering. It works like one filtering, and also the pixel, definitely the pixel sizing, and also this Doppler shift effect to and that directly relates to the azimuth resolution, the same thing. Doppler filtering, sub-aperture analysis, time frequency analysis. So all those are related, but different processing or different steps we do. So whatever these tick, we all do. These are range Doppler algorithm or range Doppler terrain correction. That is the terrain correction we use. That is called range Doppler terrain correction, and I will show you in. I showed you in last week in a software, but today I will show you in detail. It is why it is called range Doppler. So that range Doppler algorithm in Snap, what it does, I mean, these are the steps how we handle the Doppler effect. So first principle is two-dimensional frequency domain processing. 2D frequency domain. It is called the frequency domain processing, and it separates the range and azimuth compression. It deals it separately, range compression and azimuth compression. Because I think if you remember, I showed you images. One image that is compressed the far range and correct in the near range and nadir range, and gets compressed in the far range. That is because of the Doppler shift, and also that has the effect. And processing steps in Snap is range compression, range cell migration, correction, azimuth compression. All these are, Snap is the software that I used. And what are these implementation application? That orbit file application, that is it is locating the orbit. It is taking the orbit first. Applies precise orbit files. That is how it locates the data or signal, and then applies different these corrections. Update state vectors, improve geolocation accuracy. Geolocation accuracy, that, and thermal noise removal. So because of the Doppler shift and all these things, so that noise, that blurring, all this happens. So there is called one thermal noise removal. Removes the thermal noise, improves radiometric quality based on calibration data. Next is the range Doppler terrain correction. That we do in SAR, and it is called the range Doppler because of that reason. Range site and Doppler site we are correcting using DM, digital elevation model for terrain correction, correct geometric distortions, outputs georeference data. So if anyone asks that why do you terrain correction, most of the times people say to geocode the data. That is, you have georeference or ground reference. That is not always, that is obviously the output data, that is true, but it is not the only or the main purpose of that terrain correction. Normal geocoding also you could do, but range Doppler terrain correction for SAR image, it is the only thing, the best process that also do multiple things, that handles multiple things. We can see those all in softwares. So whenever we should, whenever we are using softwares, we should always look for those options, and we should connect with our theory. That is not like we will just see one procedure or one flowchart and we were just following that. Because normally many applies now also thermal noise removal, many do this step, many skip this step. So it depends, all depends how much your data is affected with noise. Do you really need that? Because of the all these steps, you are losing also something because of the correct that particular suppose noise, you are losing something also. So these steps and all those, you should connect always with the software. this is the, due to Doppler shift, and what we do in this are range and azimuth compression. Because of the Doppler shift, that near range and far range, there's frequency that change happens. So we do this. Is the range data and azimuth data. So range data, we do the range compression, that is pulse compression. And range compression, how we do, this is the matched filtering that I already mentioned you before. There is one, you can say one hardware is there, that is called matched filter. So that serves the purpose. Pulse compression also, and range resolution improvement. I am not going into that detail in showing the signal, what is pulse compression, because I think you should, in remote sensing perspective, when you're studying, we should, focus more on to physical significance rather than, it is good, but for basic studying and learning step, first to get it some theory and then some more in physical significance. Then the range compressed, it is then we apply the azimuth side compression, that is the Doppler processing, the synthetic aperture formation, that to synthesize the antenna in azimuth direction, and that is how the azimuth resolution gets improved. So finally we get this final image. So this is very broad one diagram to understand that what really happens, how we get the data from one signal, very broad. So range compression, it is like as I said, the raw data contains the chirp signals. What is chirp? It is very high frequency signal, that is chirp. There is chirp, difference between chirp and difference between signal. And long pulse is linear frequency modulation. Frequency modulation we have to do because there is something change in frequency due to Doppler. And low range resolution, first we get this. So processing matched filtering correlates receive signal with reference chirp or referenced signal. So that is what match filter does, to match the transmitted and received signal, and compress long pulse into narrow peak. Also improves, this is the way it improves range resolution. So it outputs the range compressed data, better range resolution, maintains the phase information. Similarly, azimuth compression, that is where the Doppler comes. The input data is the range compressed data now, and it contains the Doppler history and multiple looks at same target. It is looking the same target from multiple positions. Processing steps are used, platform motion, synthesize long antenna. So when you are doing in a software, it is doing, it is capturing or getting the from the metadata all the details, so many details which we can't see, but back of the software it is doing its own thing. So it's using platform motion, synthesize long antenna, apply Doppler processing. When we apply the range Doppler terrain correction, just one click, but we don't care about that what is actually happening in that process steps. Final result, we get fully focused SAR image, improves azimuth resolution and better target discrimination, obviously. So what we get finally, because of, SAR, it is not like only one step is doing only one thing. One step can do multiple things. So range compression, it improves obviously range resolution, better target separation, and also it enhances the signal to noise ratio. Signal to noise ratio, the more the better, because obviously there is noise but we need the ratio more. So we are interested into signal, not to the noise. And azimuth compression, that is better azimuth resolution, clear target discrimination, and reduce speckle noise. So azimuth compression does reduce the speckle noise. It works one kind of filtering also, you can say. So next one very major topic in SAR when studying radar SAR, these are the noise, because compared to optical remote sensing, there the noise, also the atmospheric interference, noise due to atmosphere, speckle due to atmosphere, these are important, we face that, but that does not affect that much the image as compared to SAR. SAR gets affected, it can penetrate the clouds and rains and these things, but it gets affected very much to clutter, noise, speckle. In radar, you need to understand what is clutter, what is noise, what is speckle. So, starting from clutter is, these three are different terms. Clutter is not noise, is not clutter. You have to understand. And so clutter is the unwanted echoes or reflection from the ground, returns from objects other than the target of interest, interferes with target detection. So suppose we are interested to detect flood on ground. We are sending our signal, receiving our signal, doing the SAR, all the processing, to detect we are interested only in flood water. But suppose, it is not like there is only flood water on ground, and in between the media, there are so many objects it will go through. The birds, flying, those birds and those things, and also rain, some part of cloud, and on the ground also. So many other things are there. So we are getting signals all from that. It is not like we are just targeting the floodwater, and we are mapping all those and getting this signal, receiving back the signal from all the targets. But we are interested only in floodwater. So, except the floodwater, the all other signals are clutter to me. So, the characteristics is it is surface dependent, varies with incidence angle, changes with polarization, and terrain specific. Types are ground clutter, volume clutter, sea clutter, and urban clutter. Many types. There can be other types. I told you that whatever is not in our interest, those are clutter. So if suppose we are interested into urban, then urban, the signal from the urban will not be a clutter to us. Similarly, there are so many sea and this oil spill detection, all those are, happening using SAR, remote sensing. So that in that topic, that sea will not be a clutter. We are more interested to get the signal or detect or extract the signal from the sea. So echoes from rain may be regarded as clutter when they interfere with detection of aircraft or other point targets, but they are themselves the signal of prime interest for weather studies. That is what rain can be clutter to me, but who are interested, suppose who are studying atmospheric, this interaction, atmospheric data, for them rain is not a clutter. Now comes the noise. So what is noise? Noise is different from clutter. Noise is thermal noise, system noise, quantization noise, antenna noise. These can be, these are the sources of noise, causes of noise. So the characteristics are random in nature, affects radiometric quality, temperature dependent, system dependent. The sources are electronic components, atmospheric effects, system limitations, digital processing. So the most of the noise we get from system noise, quantization noise, and digital processing. I mean, we can get noise, antenna noise, all are there. Handling methods are noise reduction filters, radiometric calibration, multi-looking system optimization. So it is noise I mean, the by filtering, this is the first and the primary one to reduce the noise. But there are other steps also from which we can reduce the noise. I mean, noise gets reduced. That already I told that because due to the radiometric calibration, noise gets reduced a little. Due to multi-looking, during the multi-looking step, it gets reduced like that. So noise happens. Noise is mostly due to, you can see here, mostly due to the system. It is related to system, not related to any target weather, not that. And SAR is so complex, and SAR has so many, I mean, if you study in detail the all the hardware part and their application, it, I mean, you have to accept some level of noise. I mean, you have to compromise to one position, to one state, that you have to accept some noise to compromise to other things. So that is how SAR works. That is why we can eliminate totally the noise. Then we have to compromise more to other things. Okay, that way it will not work. So that is why we have to accept the noise. And so after getting that, we best thing we can do is to handle the noise, to reduce the noise. We can't eliminate totally the noise, we can reduce that. So there are, we will study about various noise reduction filters and radiometric calibration, multi-looking. Yes. And because of the noise, what happens, that is called the speckle noise and interference. So speckle is the random noise in radar image due to interference phenomenon. And inherent noise-like processes which degrade image quality in a coherent imaging system. And in a ground resolution cell, the individual scatterers differ in their delay time but not recorded as different features because of the resolution limitation. Gives resultant signal the summation of signals from individual scatterers which differ in phase. This phase difference causes the interference, and due to this, resultant may vary 0 to the absolute sum of the individual signals. So local constructive and destructive interference appears in the image as bright and dark speckles relatively. It is time independent phenomena. So speckle is coherent interference of waves scattered from terrain elements observed in each resolution cell. An incident radar wave interacts with each element of the surface and surface cover to generate scattered waves propagating in all directions. Those scattered waves that reach the receiving antenna are summed in direction and phase to make the received signal. The relative phase components contain the differential propagation paths, and the SAR focusing operation coherently combines the received signal to form the image. So there is one term you can focus, that is coherent, incoherent, it is repeating. The scattered wave phase addition results in both constructive and destructive interference of individual scattered returns and randomly modulates the strength of the signal of each resolution cell. So what is really happening? I'll show in diagram. So addition of backscatter from a collection of scatterers produces a random constructive and destructive interference. Constructive interference is an increase from the mean intensity and produces bright pixels, and destructive interference is a decrease from the mean intensity and produces dark pixels. These random fluctuations give rise to speckle. So reducing these effects enhances radiometric resolution at the expense of spatial resolution. That is what I told. I mean, you have to compromise. So if you want to reduce this effect, that enhance the radiometry resolution, but at the expense of spatial resolution. We are, I mean, our the most important is spatial resolution. We need the more detailed, I mean, higher spatial resolution. The more higher, the better for us. But the way the system works, I mean, if you want to reduce that effect of the speckle after some, I mean, limit or beyond one some limit, we have to compromise the spatial resolution. So what we decide? We decide our spatial resolution to be one at one stage, and also to get to have some already the speckle effects also. So this is what the constructive and destructive interference and the signals, coherent, incoherent. So the constructive, the coherent radar waves, these are the coherent. The solid one, if you see, and the dotted. So all are the coherent. It is not, I mean, shifting. I mean, coherent means I mean you have the phase, same phase. You that is in same phase. That is called coherent waves. So when the transmitted and receiving are incoherent, then it happens the constructive interference. When that are not coherent, there is phase difference. They are called the destructive interference. There the darker pixels we get. And varying degrees of interference between constructive and destructive, it depends on the phase shift. This is from, I mean, one example of speckle of radar set 1. So speckle are here. I mean, you can see, I mean, I think I can zoom in. The speckle are like these. These are not the darker the patches, but more like, I mean, you can see one waveform of bright, some, I mean, bright patches, dark patches. So those are the speckle. Those are due to the noise, and those are the speckle. So using independent data sets to estimate the same ground patch by average independent samples can effectively reduce the effects of speckle. So averaging. One thing, I mean, the main thing, that is what we average, because multiple pixels have different. So we distribute. Okay, the more, I mean, maximum we can do is that distribute the noise effect or the speckle to all over. So multiple look filtering or multi-look separates the maximum synthetic aperture into smaller sub-apertures, generating independent looks at target areas based on the angular position of the target. Therefore, looks at different Doppler frequency bands. Averaging incoherently adjacent pixels. Reducing these effects enhances radiometry resolution at the expense of spatial resolution. So how it comes? So it looks granular noise pattern and constructive destructive interference inherent to coherent imaging, and we call it salt and pepper. The noise in SAR term, it is called the salt and pepper, grainy or granular noise pattern. The grainy or salt and pepper, like the grainy texture, that is how we identify the speckle or noise in SAR. The characteristics are multiplicative in nature, follow statistical distribution, resolution, cell dependent, and preserve edges. So effects are reduces image quality, affects interpretation. Definitely we can't, I mean, say really that is it the backscatter from one's target, any target, or any, or the noise. So impacts classification, definitely hampers feature extraction, the same. So reducing methods are multi-looking. It does it, I mean, all the purpose to some extent. some other filters, Lee filter, Frost filter, Gamma Mac filter, non-local Mills filter. These are the SAR filters. Okay. So important considerations are trade-off between speckle reduction and spatial resolution. This is the most important. As I said that we have to decide how much we will compensate our spatial resolution to clean the speckle. So that is what also comes with experience, that to what extent we can keep the speckle. Preservation of edges and features. Edges are very important to any remote sensing image. Maintenance of radiometric information and processing time requirements. So multi-look, we already saw that what multi-looking is really doing. And look means each of the sub image used to form the output summed image implemented in the processor. So basically it is one ratio, and with the incidence angle we will see later today class some numericals on the equation, how we can decide multi-look for different sensors. So we get one single look image, we have to do the multi-look to get the range and azimuth pixel size, and this way the noise gets reduced a little, and we get the all the pixel size from near to far range to our desired size. So these images here it talks about the image will contain speckle but have the highest achievable resolution, and that is the highest achievable, that okay it will contain speckle but it will achieve the highest resolution also. And independent images of the same area can be formed in the digital processing of SAR data by using subsets of the signal returns, and these images are then averaged to create a single multi-look image, and resulting image has lower resolution but reduced speckle. So we compensate little bit in our spatial resolution to get reduce the speckle. Now speckle, we will see different filtering procedures, speckle filtering, and this is how we the original image and one after the filtering, the filter image. You can see the change in both, change in resolution. It is higher resolution, so clear, it is blurred, lower resolution, but the speckle is cleared now. Here this it was speckle, but we compensated little on the resolution, spatial resolution, but we also get reduced the speckle to some extent. In glacier also you can really now see the difference in speckle. This is the grainy or granular effect due to speckle, but after filtering you can see it is the snow cover, that is why we can understand the smoothness, and after the speckle filtering you can see the now the smooth surface, snow surface. So this is what SAR image, why it SAR image, that is why looks so grainy, and it is called the salt and pepper noise. Salt and pepper noise it is called. So after the filtering it reduced the salt and pepper effect and gets one smooth, and also the spatial resolution definitely gets reduced. So there are speckle reduction, radiometric enhancement, and this is one method of speckle filtering. So why speckle filtering? Often the reduction of speckle is desired to improve classification for enhancement. What is the ideal speckle reduction filter? Non-adaptive filters and adaptive filters. That is the Frost, Lee, MAP, Gamma filters. To reduce speckle, adaptive filters should be used rather than non-adaptive filters on radar imagery. So we are most interested in the adaptive filters. FFT filters are, FFT means the first Fourier transformation that works in the Fourier series. So that are not in the SAR scope, we will look into the adaptive filters for the SAR filters that take into account the local properties of the terrain backscatter or the nature of the sensor, whereas non-adaptive filters do not do that. So spatial filtering is a pixel by pixel transformation which depends on the digital number of surrounding pixels. Spatial filtering is a context dependent operation that alters the gray level of a pixel at any location according to its relationship with the digital counts of the pixel in its immediate vicinity. Spatial filtering refers to separating out some features. So it is, I mean, it works with the, you can say the main principle is to distribute to all over the adjacent pixels and then adjacent, then all over the image. So how we will do the distribution, that is the different filtering techniques, but overall we are doing the distribution of the concentrated speckle or noise. That is the main thing. So that is why if suppose one pixel we want to reduce the speckle, its adjacent pixels definitely needs to be, comes into the picture for the calculation, because that is how we are distributing to all over the image pixels. So this is one image showing the pixels in black and white. So its task is to either emphasize or de-emphasize image data of various frequencies. Essential spatial frequency enable the tonal variation per unit area of an image. So an image area of high frequency is totally rough. This signifies the digital number values in this area changes abruptly over a small number of pixels. So in view of the application, the spatial filtering are categorized mainly the, other way, the noise removal also, edge enhancement or edge crisping and edge extractions also. So depending on your study area, it can be this many times people are more into keeping the noise, but edge enhancement they want to do, and edge extraction also, that has different application. And keeping the noise, in SAR it is many we do. We don't do the noise removal steps. We do multi-looking definitely and range Doppler, but not any noise filtering. Many times we do, because due to that we have seen that we lost information, other scattering information we lost. So we decide to keep that noise, and we don't lose the information also. So it depends on the application and our target. So filtering, so now we have to distribute the noise to all over the image pixels. And how it is done? It is performed by using convolution windows. Basically window of any size we can decide, depends. It also depends. So these windows are called mask, template or kernel. That kernel, the windows or the kernel, it has the same concept how we, in our technical terms we do. In machine learning also the kernel, the windows, those as concept, it is the same. So the window is moved, or the moving window we call it, over the input image from extreme top left hand corner of the scene from pixel to pixel, performing discrete mathematical function transforming the original input image digital number to a new digital value. So first it will move along the first line. As soon as the first line is complete, it will restart from the next line and continue till it for covering the entire image. To carry filtering, a process known as convolution is performed. So convolution windows and the convolution term comes to, so that we distribute, we take small pixels of certain size, suppose 3 cross 3, 5 cross 5, depends, 7 cross 7, and we do the, because we are interested into one pixel and then its adjacent pixel. So how larger size, that depends. So convolution may be defined as a simple mathematical operation which is fundamental to many common image processing operators. Convolution provides a way of multiplying together two array of numbers, generally of different sizes but of same dimensionality, to produce a third array of number of the same dimensionality. In image processing context, one of the input array is normally a gray level image and the second array is usually much smaller and is also two-dimensional and is known as the kernel. That is what we call the window or the kernel. So one is our image, gray level image, that is the image. The second array that we will be moving all over the image and is usually much smaller. Suppose our image is 2000 by 2000 pixels and our window will be 3 cross 3, 5 cross 5, 7, maximum 9 cross 9, like that. So it is usually much smaller and it is also two dimensions. It should be 2D array. I mean the x and y direction. You can say the range and azimuth direction, our 2D direction, because our image is 2D. Whatever raster these we at first, one image we work in 2D. So the dimensions should be same. And that window, moving window, is known as the kernel. So the convolution is performed by sliding the kernel over the image, generally starting at the top left corner to move to the kernel through all the positions where the kernel fits entirely within the boundaries of the image. So it is very important. So it should fit. It should not miss any image, and that is how we decide the kernel size also. And each kernel position corresponds to a single output pixel, the value of which is calculated by multiplying together the kernel value and the underlying image pixel value for each of the cells of the kernel and then adding all these numbers together. It depends how we are averaging all the pixels. But every kernel, every window, every movement, it is deciding or working on one pixel only. And how we do, here it is showing, okay, the middle pixel we got this kernel. It is one 3 cross 3 window and it is deciding, performing some operation and the output. So middle value will be the 16. Previous it was 8 but 16. But how to do this operation on this pixel 2, the top left corner or the right left, whatever. So there if you move this window 3 cross 3, it will get value this side, right and bottom, but not left and top. There the pixel, this kernel, these pixels will be empty, but this should be processed now. So what we do there, we assume one number, any, not 0, because 0 has effect with other. We will assume in one number, same number to those pixels that are void. But we must fit the 3 cross 3 kernel. We must have some value to those. So here it is showing that same thing. If the image has m rows and n columns and the kernel has m rows and small m and n columns, then the size of the output image will be this m minus m plus 1 rows, and this is, you can test anytime. So this will be the output image row. That is why we should handle cautiously. It is not like we are just inputting and doing the thing and outputting. Many times people, students, they come and they told that there is extra row, extra column added. Why? Because of that operation. So after that, how, I mean, if you want to trim the, I mean, how you treat that edges, it depends. You have to look and be cautious with that. So the value of the bottom right pixel in the output image will be given by this is shown like that. So mathematically a convolution can be written as this, where I runs from 1 to this and it is 1 to this. So it may be noted that many implementations of convolution produce a larger output image than this because they relax the constraint that the kernel can only be moved to positions where it fits entirely within the image. Instead, these, I mean, that is what I told. They relax the constraint. I mean, there is no constraint that it will move till the boundary of the image. It can, because you have to process the boundary pixel also. So you will skip the boundary, you will cross the boundary, then take that, and the void, whatever digits it is not getting, you will fill and assume one value and fill those and do the operation. So that is how it is adding the side by rows and also the columns, whatever. That is how it gets added, because after the processing some value will be there. So instead, these implementations typically slide the kernel to all positions where just the top left corner of the kernel is within the image. Therefore, the kernel overlaps the image on the bottom and right edges. And one advantage of this approach is that output image is the same size as the input size. So this is how also many times we do. So unfortunately, in order to calculate the output pixel values for the bottom and right edges of the image, it is necessary to invent input pixel values for places where the kernel extends off the end of the image. Typically, pixel values of 0 are chosen for regions outside the true image, but this can often distort the output image at these places. It is said here, but we don't take 0 because 0 has different effect. If we multiply something 0 with some number, it gets 0, but better to take any number. Therefore, in general, when using a convolution implementation that does this, it is better to clip the image to remove these spurious regions. So after this, we clip that extra row and column. Removing n-1 pixels from the right hand side and m-1 pixel from the bottom will fix things. So whatever extra row and column things it is adding, we will remove that. The kernel window size may be rectangular or square, but for SAR, whatever filters, we consider it as square pixel size, because that way that has other reasons also, and it is the best to get take the square pixel size 3, 5, 7, 9. So each pixel of the window is given a weightage. And for low pass filters, all the weights in this window will be positive, and for high pass filter, all the values may be negative or 0. But the central pixel will be positive with higher weightage value. In the case of high pass filter, the algebraic sum of all the weights in the window will be 0. So what filters to use, it all totally depends on our data. Many types of mask windows and different sizes can be designed by changing the size and varying weight within the window. So these all will have effect also. So many research are there to on these, that okay, we changes the window size from 3 to we increase the window size, what are the effect output, and decrease the window size, what are the output. So the simplest form of mathematical function performed in filtering operation is neighborhood averaging. That is the simplest one. We average with the neighborhood pixel. Another commonly used discrete function is to calculate the sum of the products given by the elements of the mask and the input image pixels digital number at the same point, and use this sum as the output digital number of the central pixel digital in the moving window. So it gets, that is the average. We do just the average and assign that only to the central pixel, not to the all value. So what what are the main feature of noise? So again, noise is a term used to designate unwanted signal recorded in the image that are unwanted. A noise is an image may be detected as isolated pixels having no correlation with its neighborhood pixels. That is what how also noise we can detect noise. That some abrupt change, abrupt high or low change in noise, because when suppose we are looking at one flood pixel, water pixel, it will have some range, certain some area it will have some range, not like okay, it is the range, it is ranging between 1 to 10 suppose value of pixels, but certain one pixel is 1000, and it happens in practical. So that is that due to noise, that is not the actual target scattered. So it may be present in the image either due to pre-processing of data, sensor characteristics, or channel errors. If noise is present in the image, then the corresponding histogram will not be Gaussian in nature, and the image is generally found unsuitable for analysis. Because obviously, if there are abrupt changes, then Gaussian, that Gaussian curve, what we say, it will not be. There will be multiple, the curve. So hence noise should be removed from the images so that subsequent enhancement, registration and numerical analysis can be performed on image. And it can be two classes: independent noise and noise which is dependent on the image data. So independent noise, obviously the system, we have not talked about the how to reduce the system noise, the antenna noise. Those have different domain. We are only interested with the system noise. And the impact of the noise on the image is often described by the signal to noise ratio. That is, in mathematical term, how we handle the SNR. So in many cases, additive noise is evenly distributed over the frequency domain, that is white noise, whereas an image contains mostly low frequency information. And hence the noise is dominant for high frequencies, and its effect can be reduced using some kind of low pass filter. This can be done either with a frequency filter or with a spatial filter. Often a spatial filter is preferable as it is computationally less expensive than a frequency filter. Frequency filter and these things are mainly, you can say, hardwares, and SAR itself, the system, the total system is very costly, and the mission are very costly. So when it is better to process after getting the signal, process that, rather than adding another hardware also, because we need to keep that in mind, that the SAR and hold the system, whatever is flying, the sensor hold the system, it is lightweight, because obviously due to all the limitations. So smoothing filters are designed to reduce the noise, detail or busyness in an image. That again, busyness relates to the grain, the granular or the salt and pepper, that effect. If multiple copies of the image are available or can be obtained, they can be averaged pixel by pixel to improve the signal to noise. However, the enhancement techniques developed for this can be performed on a single image. In this case, typical smoothing filters perform some form of moving window operation, that may be convolution or other local computation in the window. So there are many more. The starting main, we will cover the mean filter, weighted mean filter, median filter, mode filter. What is mean? That is the basic, the averaging filter. So in this technique, each pixel within a given window, say 3x3, is sequentially examined, and if the magnitude of the central pixel is significantly different than the average brightness of its surrounding pixel, then the central pixel replaced by the average value. So it is detecting that is it any abrupt change in that pixel. If that is the change, then it will replace with the average value. Weighted mean, the similar, but it is the weighted one. So is often used in which the weight for a pixel is related to its distance from the central pixel of the window. So it consider the distance, and that is that is very important in our context, in our remote sensing context, when we deal with our ground data. So for example, if the processing of boundary area of any region is to be undertaken, then the different weights inside and outside the boundary are assigned such that the best results for boundary as well for region can be obtained. So it takes into consider the proximity of the pixels also. Median filter, it uses median rather than the average of the neighborhood pixel of a given window. So the median of a set of numbers is that value such that 50% of the number are above and 50% are below it. It is considered to be superior than the mean filter primarily due to two reasons. First, the median of a set of n numbers is always equal to one of the value present in the data set. Second, median is less sensitive to errors or to extreme data values. So what due to mean or and weighted mean also, we are assigning totally new value that does not come from the any of the pixel value or the neighbor pixel. So it is totally changing. You can visualize it is changing the image pixel, but we don't want that. We want our values. So median, when we do the median filter, it the whatever value it is assigning the after the speckle after this filtering, that value will come from the set of the pixels value. So that way our it conserve the character of the image, okay, the properties of the image. And it is less sensitive to extreme data values also, because after mean filtering, the new value we are getting, that can that also depends on the outside and different pixel values, and we can get the many times extreme values also. So median filter is conceptually simple. A median filter is inefficient to implement because sorting of the pixel is in ascending or descending order is required. However, it is one of the best noise removing and edge preserving smoothing filter, but thin lines narrow than the dimension of the filter window may be removed. This filter has no user defined parameters. So when there is thin line, suppose one river is going and it will come as very thin, suppose 2-3 pixel width, it has very thin narrow canal and these things, then these can be lost due to if we apply median filter. Mode filter, in this technique the central pixel is replaced by its common neighbor. So this is particularly useful in coded images such as classification maps in which the pixel values represent object levels. And averaging labels makes no sense, but mode filters may clean up the isolated points. It produces irregular shifts in edges which makes them appear ragged. So every filter has its own positives and negatives. It is up to us where we are interested, what is our purpose we are focused into, and how our data is. So till now I have not discussed the in numerically, because I think just to discuss numerically it will not clear the this filtering mainly, it will not clear the concept, rather solving numericals, showing some numericals. So I have kept numericals from multi-look and from the range and azimuth compression or calculation, and also from the filtering. So from multi-look we can expect this type of images or this type of problems. So if a SAR image has 30-meter range resolution and 5-meter azimuth resolution, if 6 looks are applied in the azimuth direction, calculate the final azimuth resolution and the new pixel spacing. So it is given now the 30 by 5 1 pixel, and we are applying the 6 1:6 the multi-look ratio. So final azimuth resolution will be the original resolution into the number of looks, that is in azimuth, and so it is 5 into 6 30. So new pixel spacing will be 30, and the final will be, there was the range was 30 into 30, that is. Next is one single SAR. It has dimension in pixel, given in pixel 12,000 into 15,000. If we apply 3 cross 4, 3 in range, 4 in azimuth, multi-look, what will be the final image dimension? So here you have to understand it, what it is doing. It is not multiplying. Okay, new range dimension is the pixel by 3, and new azimuth dimension is the by 4, the azimuth look. Final image size is 4000 into 3750. Why it is not multiplying? Why it is dividing? Because by multi-looking, obviously we are making the pixels almost square. That is our focus. But also we are improving our spatial resolution. So improving our spatial resolution, that way the improving in the sense the pixel sizes will be smaller, and that way this we do the division. Next is a SAR image as initial ENL, that is equivalent number of looks of 1. If 2 into 3 multi-looking is performed, calculate the final ENL and speckle reduction factor in dB. So final ENL will be the initial ENL, that is 1 into range into azimuth. So final looks will be 6 look, and the speckle reduction factor will be the 10 into log, that is how we calculate in dB, log 10 base of the number. So the speckle reduction factor in dB, it will be 7.78 dB. And another, it has ENL is equal to 1, has a measured standard deviation of 0.52 in a homogeneous area. After multi-looking, you want to reduce this to 0.25. How many looks are needed? So for multiplicative speckle, standard deviation reduction will be root over 1 by L. L is the number of looks. So it will be, we put the digits, then L will come something 4.32, and we will increase this. So round up to 5 looks needed. We will not decrease this to 4, we will increase this. Now comes actually how we calculate the range and azimuth. So SAR image has ground range resolution 25 meter, incidence angle 35 degree, slant range resolution 15 meter, and azimuth resolution is 5 meter. So if we apply 1:4, 4 looks are applied in azimuth direction. The multi-looking look is 1:4. So calculate the final azimuth resolution, calculate the final ground range resolution, the slant range, and what would be the square pixel size in ground range. Basically all the. So final azimuth resolution will be the original into number of looks in azimuth. So 5 into 4 is equal to 20. But in ground range resolution, as it is not affected by azimuth, azimuth multi-looking, it will be 25 meter only. Number C, calculate the slant range resolution. And slant range also will remain same as it is not affected by azimuth multi-looking. So, and the main equation we have to remember, that is slant range is equal to ground range into sine of incidence angle. So, and we can verify if it works. Now to get the square pixels in ground range, current pixel size is 25 meter in ground range, and that in range, and 20 meter in azimuth. So additional looks needed in azimuth is 25 by 20, that is 1.25. Round up to this thing, so it will come to 2. So final pixel size in will be looks in 5 looks, 25 meter into 25. Next comes some numerical on image filtering. So this type of if we solve this type of numerical questions, it will be very easy, better to for clarity. So one 3x3 window or kernel, it is given. If the center pixel 55 is on the image edge and you need to apply both mean and median filtering, then calculate standard mean and median, calculate edge adjusted mean and median, and compare results and determine which better preserves edge information. So standard calculation mean, we will take all the 9 elements average, and median we take the middle one of the all the pixel values. So edge adjusted excluding right column, mean will be this 1824 plus 18 plus 24 plus 15 plus 55 plus 20 plus 26 by 6. So this will be the filtering, that is excluding the right column. Median will be again, and edge adjusted, so the conclusion which better preserves the edge information. So for mean we can see that it comes to 26.33 and median comes to 22. So edge adjusted better preserves the information than the only considering the valid pixel. Now comes another numerical, that is one 5x5 window has center pixel value 100 with standard deviation sigma is equal to 20, surrounding pixels average 60. Now here average is given. So using calculate weighted mean with weights w is equal to this, where d is the distance from the center, calculate adaptive mean filter where k is equal to 2 in formula something this, and there is some noise variation is given, variance is given. So weighted mean calculation, what is the center weight is equal to 1, adjacent pixel weight is equal to 1 by 2, and corner pixels weight are 1 by 3. So weighted mean will be all the weights of the weight of the average is given, so weight of the all, so that will come into this. Adaptive mean will be the equation, according to the equation it will come to 80. So you can refer all these from the slides. This one is the main very important problem. So We have a 5 cross 5 window centered on a pixel with the following intensity values that are in dB. So local mean in window is given 35 dB, noise variance, local variance are given, number of looks is given, mode filter threshold is given. Calculate the mode filter value for central pixel, the leaf filter value using k is equal to 1, and compare both results and explain which better preserves the point target. So first one is the mode filter value for central pixel. Mode filter threshold is given 1.5 into the mean, that is the 35, so it comes to 52 something dB. Count values above threshold, that are these above the threshold, that is given, that comes into this 52.5. so mode value will be 54 dB, that is the most frequent high value. Now the leaf filter, calculate damping factor, there is the equation. So local variance is given, and according to the equation we got this, and leaf filter equation according to these are equation. I have not mentioned separately. If you do that directly from the example, you can see. So comparison, you can see the change. So mode filter gives the 54 dB, leaf filter gives 56.2 dB, so original value is 58 dB. So these central pixel, when we treat with filtering, it gives us these type of values. Due to the mode filter it is 54 and leaf filter, and it is up to us which one we want to apply. Now comes one SAR image as original resolution is 10 meter and speckle sigma is 0.3, requires speckle reduction 50%. So calculate required filter size and new effective resolution and optimal filter weights to minimize resolution loss. So required filter size is n is equal to 1 by target sigma ratio square, that is equal to 4. So minimum 3 cross 3 window needed. That we take in odd numbers, that is 3, 5, 7. That has also some reason. Normally for any purpose, not for SAR only, these windows we take. So for when it comes to 4, we will consider this as 3 cross 3. Now we will take the downside value. We will not take 4 as 5, we will take 4 as 3. So new effective resolution will be the root over of 10 square to 3 into 10 to the power this. So these all are given here. New effective resolution will be this, the original resolution, and this. So optimal weight center is equal to 0.5 of the adjacent, because the required speckle reduction we took it as 0.5, 50% it will reduce, 50% after reduce. So optimal weight center will be this. Now comes the final. I kept it as one bigger problem on the filtering. So the image is given, this is the image patch thing, it overlaps, and this is the kernel window. We want to do the filtering. We will move this kernel over this one by one, and we will do the. So given a 5 cross 5 SAR image patch, intensity values with a specialized filter kernel with this 3 cross 3, calculate the convolved value for the central pixel, that is 200. This one is 200, the digits come on lower side. The edge preservation index EPI, the is equal to, it is given the equation, and compare with a simple 3 cross 3 mean filter result. So center pixel convolution values involved in 3 cross 3 convolution around 200. How we calculate that, that is we calculate, we move that over this. So we got first one is 155 into this first one plus second one is 1. So basically it will multiply on its positional values, the image values and the window kernel value. It will multiply and summation, take the summation, then it gets this value 186.3. So central pixel convolution, central pixel comes to this. Instead of 200, it comes to 186.3. EPI, the edge preservation index, it comes to, according to the equation, some this digit. So compare with the simple 3x3 mean filter result. So one mean filter result will give this by the average, all those things by the average pixel. So weighted and the average pixel. So the specialized kernel better preserves the original value, because using the kernel we got 186.3 and with mean we got 176.2. So original was 200. So we got the higher side, that is one, using this weighted filter we got the better. So better preserve the original value while still reducing noise, demonstrating the advantage of the weighted convolution over the mean filtering. So till now I have discussed the numericals. Today revised some theory and the numericals. Now I think I will show some processing on the software. Already saw the Snap software last week, that is ideal for SAR image processing, very basic, and we processed few also images, and we processed Sentinel-1 data and allos2 data also, and we did some pre-processing. So we did the, for Sentinel-1 we did the split orbital and then the apply orbit file that we studied today, then the calibration, that is the radiometric calibration, that also we studied today. The debust, these are for particularly for Sentinel-1 data. As I showed you, it comes into swath, so the lines are there, so we have to remove the lines. Then again some multi-loop comes, then some speckle filtering we did. So I think I will show you the speckle filtering today again, and what are the options there. We'll go to radar and we'll go to speckle filtering. So single product speckle filter, we'll click, we get these options. Is the boxcar filter, boxcar also another, averaging, median, frost, gamma map, Lee, refined Lee, Lee sigma, done, these all. Normally, I mean, refined Lee and refined Lee are the good compromise for any window, any image basic filtering technique. So you'll select the refined Lee, suppose, and if we select only the Lee, it will ask for the window size. We can decide the window size here. And also, suppose if we go for median, then it is asking for window size. Suppose we are taking it as 3 cross 3. These are the two intensity in sigma dB values. We'll fix our output, get our speckle. We can change median. Look, we already did, and one thing in software, it will calculate by its own the multi-look, but many times it does not calculate that properly, because it is up to us that what resolution we want, what pixel size we want. So we can calculate and we can multi-look that way. So let me show you. Suppose wage band, this is the Delhi side, and I think I should better show you the PV. The water will be seen, very good one in VV polarization. So the median filter gave us this image, one patch. This is the Delhi city and the Yamuna river is going. Now if we suppose want to refinedly, this is the one we normally do, and is there. The first one is more grainy, second one is more smooth. It has different change. You can see second one is brighter, first one is second one, this one is darker, the refinedly first one. So the values changed, just to show you that. Now we suppose we are doing the terrain correction. After this we did the terrain correction, that is the range Doppler terrain correction. There is the geometric, there are many more. Range Doppler terrain correction there. In parameters, now we can see we already multi-looked the data, that is why it is coming into this pixel size 13.9 into 14.6, and it is using this SRTM 3 second this free 30 meter DM, and we are using the bilinear interpolation resampling method. Map projection we can we can save many times. We want to save, work with the incidence angle also. So that time we, and also layover, shadow, mask, all these. So we can click any of the projected local incidence angle, and incidence angle from ellipsoid. So we are into this local incidence angle, and we can so now I got the terrain corrected. That is this. Now it is aligned with the what, ground. See here you can't see, the actual latitude, longitude, and here you can see how it is now aligned. And to show some other things, you can look at the metadata. Now you can see the range and azimuth. Dux is here, range is 4 and azimuth is 1. So it is 4:1 now. And it is took the ATM zone 43 of Delhi. DM it is using SRTM 3 second DUM. And this is the way you read SAR data, because time to time you have to check that is it doing the right thing. Now for allows to data, this also we processed. Suppose we did the calibration and speckle and terrain correction. It was the quad pole data. So if we plot, we see the HH band image. Let's see, and you can see it is the Japan data on Japan, and the you can, from here you can see this is the location, this is the tile we are looking at. This is the HH location, HH image. This is the HV, and VH. These all are intensity image. That is the in dB. And we can plot the histogram from here also. Here, this you can just simply click and hit the refresh. So it comes in this here, dB in intensity. So it is the log 10 log 10 that comes in dB. For HH band we are calculating the histogram. It's taking some time. It is very big image tile, that is why it is taking this time. But normally what we do, we subset. After this we subset our area of interest, and then we can compute the histogram and all these things. Now we can see the dB values. So it ranges from 0 to 45, and this is the pixel. But it is the Gaussian curve. Okay, it is the Gaussian curve, and it mostly broadly ranges from -35 to 15, the values. And suppose if we want to get the histogram of, I can show you this. It has all the pixel values, concentrated in 0. Did not come correctly. Min max we can set. How it is showing the dB values. For that it came properly. So suppose for VB, and also we can plot the scatter plot also here. Cross this, and we just plot this one, get the histogram and the scatter plot also. So this is the scatter plot. I think it, in software it gives you, in very basic one notation, not very, but if you control the bins, and the range xy, then you will get. So scatter plot basically shows us the distribution of the data along its axis, and you can see the ranges in dB and the distribution. So this is how initially we read the data in software, then we can play with the image and data according to our wish. This is how we do the speckle and handle the speckle. filtering and do the range Doppler terrain correction and all other processing. And we have studied today the difference of noise, clutter, speckle, and saw few numericals. And if you have any doubt regarding numericals and anything, you can mail me. And also we saw few of the examples that I showed already in last week, and today also showed the examples and how we first read the data in Snap software. So we will see in the next week the coming syllabus, whatever there it will be. So for today I think this is for today, and if you have any question you can ask now or you can mail me also. I think it is for today this are, and always the I refer these books, these three books I always refer. The last two are the major for SAR to read and to understand basics. That's it for today. Thank you.